Today we have our third lecture, and we are continuing with learning some tools of machine learning. So basically, that's tools that we will need to use in the following lectures, some machine learning libraries like sklearn and so on. And the previous lecture, I told you a little bit about Python. So hopefully you know now at least something about some basics of the Python, some syntax of the Python. And today we start our first library that is very useful, and you will probably need it if you do anything with Python, be that, I don't know, machine learning or some scientific computation. So that depends on what you will do in future. But anyway, I think that you will need this library. And the name of this library is NumPy. So NumPy is the library for mathematical calculation, and it's, I would say, a central object of this library is so-called NumPy array. So this is the structure to keep some data, data in form of array. It may be a multi-dimensional array, and it allows you to perform a number of different operations, mathematical operations on this array very quickly. Why? Because NumPy basically lives in the form of compiled libraries. So it was written in some sort of, I don't know, C or C++, something like that. And when you are doing something with NumPy, the basic idea is that you collect your information, you send it down there to the binaries. It performs all the operations that you wanted from the NumPy array. So I don't know, some adding some vectors, multiplying. There's a whole lot of operations from linear algebra and so on and so forth. It performs all that operations, and then it returns you to the Python. It returns you the result of these operations. And this is very useful because that allows us to perform a number of operations much quicker than we can do with just bare Python and with lists of the Python. So you can think about NumPy arrays as some sort of substitution for lists in Python, but they work much quicker. And of course, they have some sort of properties that you may want to know, because of course they differ from lists in Python. For example, you can't keep their elements of different types and so on. And today we are going to get through some of the properties of these NumPy arrays, and I will show you some of the operations that we can perform on these NumPy arrays. So let's start with the very basics. And here is the code that creates NumPy array from the list. I put some numbers in this list, and I told, please create me NumPy array. You can recognize here importing. So we were talking on the previous lecture about importing different modules. I am importing NumPy in my code. Moreover, you see syntax like importing as NP. So I'm giving it some shorthand. So I don't want to write everywhere NumPy dot something. I want to write in NP dot something. In this model, there lives array. It's NumPy array. And here I am calling constructor. So the function init, as you remember from the previous lecture. And I pass into this function some sort of list. This list will be transformed into the NumPy array, and then I can work with it. Here is an example of the visualization of the NumPy array. This is not a standard visualization, so this one I wrote specifically for you. So you won't see that in, I think, any other sources. So I guess I need to give you a few explanations. So what is it? The NumPy array It's a this is a multi-dimensional array. As you see on this picture, you can reference any element in this multi-dimensional array. Of course, I can draw for you, I don't know, a 4 or 5 dimensions or so on. So I'm using some sort of wrapping to represent that we have multi-levels in the array, these multi-dimensions. So when I am referencing some element, I'm some sort of unwrapping that element layer by layer by layer. So for example, to get to the element 9 in here, I need to unwrap this box number 1, then number 0, then number 2. So if I will reference this element from the array, I will say, so I need some sort of x, and in square brackets, I will put 1, comma, 0, comma, 2. And that will reference for me this element 9. As you see, this object has different properties. So here is the number of dimensions, so 3 dimensions. Shape, very nice property. You will use it a lot. It tells you basically what are the sizes of the array. So how many elements do you have in there, and how do they look like? Size gives you the overall number of elements. Type, it's a very nice property. It tells you what is the type of the elements in the array. All the elements in NumPy array should have one and the same type. People are trying to create NumPy array with type of like something like int64, so integer values, and then put into there, I don't know, some floating point numbers. That's no good. If you're trying to do that, you're going to get into some sort of troubles. Maybe it will put the data in that array, but it will, I don't know, remove everything after the comma. So if you are trying to put there 0.5, you will get 0. So that's no good. Okay, what else? Types. You may have a whole lot of types in NumPy array. Here is the table that describes what types you can have there. So different types of integer numbers, floating point numbers, even some complex numbers, and so on. So you can check that. Okay, some simple operations that we can do on the NumPy array. So first of all, what we want to do with the array. So we want to know how to put some information into there and how to get some information from there. So the basic operations are some sort of indexing. So I can access, for example, a single element from the array. So here's an example for you. So array x1. I just created some random array with the help of NumPy randint function. So here is some sort of hint for you that NumPy arrays, NumPy module contains not only a class of NumPy array, it contains many interesting functions. Here is the submodule random, and it may be of interest for you if you are trying to get some random numbers, or if you are trying to do some random permutation of something and so on. So that may be really helpful. Here I am visualizing this array, so you can see that the numbers on top and on the bottom, these small numbers, they designate indices that you can use to access the exact element from the array. And here is an example. So if I call x1 square brackets 0, I will get number 5. Why 5? Because cell indexed by 0 contains number 5. X of 4 is 7. As you see, it's 7. X1 from -1. The same idea. Well, this is a very interesting idea that many other programming languages, I guess, are lacking. So it's a really nice thing to have. You can index your array backwards. So if I don't know what is the length of my array, and I don't want to check that, I don't want to do all that addition, subtraction, and so on, I can just index my elements in the array starting from the last element. The last element gets index -1. If I'm getting the fourth last element, it will get index -2, and so on and so forth. So if I want to just get some sort of tail of my array, I can use negative indices to get all these numbers. So starting from -1 and so on. And here's an example for you. I'm indexing elements -1 and -2. And once again, I get 9 and 7. Okay, so you can index your array from both sides. So from the left side and from the right side. Starting from the head of the array, you are indexing from 0. And from the end of the array, you can index starting from -1. Okay, what else? Different types. I have already warned you that NumPy array has a certain type. This means that every element in the NumPy array should have the same type. What it means in practice, when you are doing something with NP arrays, you may get into trouble if you mix up that types without realizing what are you doing. So I have already seen that in the code when someone tries to do something with the NP array, and he wants that array to be some particular type. But he doesn't, I don't know, he doesn't declare that somewhere. He doesn't write for in the constructor of the NumPy arrays that he wants that sort of type and so on. He gets a different type, and then he gets all sorts of errors based on the fact that he's putting, for example, floating point numbers in integer array. Here's an example for you. So I have an array with the type integer 64. So just integer numbers. It perfectly does the job. So it contains some sort of integer numbers, 5, 0, 3, and so on, so on. And now I want to change something in that array. And I'm trying to set x1 equal to 1, 2, 3, comma, 4, 5, and so on. This is a floating point number. When you are setting that into array, into NumPy array, you don't get an error, but you get your number truncated. Arrays do not change their type on the assignment operation. So if you are trying to do some sort of assignment, when you are putting some data into array, please do not expect the array to change its internal type to match your data. That's not what's going to happen. How do you think why? Of course, we can program whatever we want. So of course, I can create NumPy arrays that will change their type if I am assigning to integer array some floating point number. Okay, why nobody did that?
For safety reasons, maybe? Just to ensure less amount of bugs in code.
Well, not safety reasons, but I heard a good answer from auditorium that that will take an enormous amount of time. If you are you have I don't know, some large NumPy array, I don't know, 1 million of elements, and you're trying to assign one element with a different type, you will need to change type of all of that elements that you have. That is copying an enormous amount of elements in the memory. So it's a very large chunk of the computer's memory. And copying any data in computer's memory, it takes quite a lot of time. So we don't want to do that. And we will see when we walk through some operations that we do on NumPy arrays, we will see that creators of these arrays were trying to minimize the number of memory copies as much as they could, because this is time consuming. So we don't want that. That's why if you have some type of NumPy array, it is fixed and you are working with that type. If you want a different type, that will cost you a lot of time to convert all the data to a different type. And that's why you should do that consciously. So you should create a new array, you should assign it a new type, and then you copy your data into that array. So that's the way you should do that type changing consciously. Okay, one more example, two-dimensional array. So here is a visualization. We have two-dimensional array. I'm trying to index an element of a two-dimensional array. Here is the code that shows you how to do that. So you are basically using comma to separate different indices, and you can put them into square brackets. So I'm having here x2 array. I'm using square brackets, and I'm indexing element 0, 0. Which one is this element? So in my visualization, you can see that we are unwrapping box by box. So the first index is 0, so I'm unwrapping box 0. So here it is. The second index is 0. Once again, unwrapping box 0. Who's there? Number 5. 2, comma 0. Okay, box number 2 and box number 0 in there. So here's number 2 and so on. Once again, you can use negative indices to index from the end of the array. You can use that on any level that you want. So along any dimension of the array, that will be perfectly okay. Okay, now I'm copying arrays. I can use function copy to copy all the data from one array to another array. And here is an example when I have copied array and I have assigned a new value to one of its elements. You see that the copied array has changed. Our initial array did not change. Once again, you can remember from the previous lecture that when we are doing all that sort of operations in Python, we will most likely get, I don't know, that internal references to the array from different names, but to this array. And that's why you need, sometimes you need to perform explicit copying. If you want to say that you want a new array, you don't want to work with the old array. Slicing. We have already had that sort of syntax with Python lists. So arrays are very similar in their syntax to lists, at least when we are accessing elements or when we're trying to make some slice and so on. So here's an example for you. I'm trying to slice an array. Array contains number 0 to 10, and I'm slicing elements from 4 to 7. Once again, an interesting question for you. What are the indices of the elements I get in this slice? 4 to 7. There's one small caveat I want you to remember. Yes, please. Yes, 4, 5, and 6. Absolutely correct. We don't take the 7th element. And we had the same, yes, one more correct answer in chat. Good. So once again, we remember that the upper limit is never reached. So if I'm slicing elements 4 to 7, I don't get the element with index 7. I get element with index 6, and that's all. Okay, here are few images that illustrate how do we perform that slicing and difference and some different syntax. How do we can get all that sorts of slices? For example, I told you that you can not write 0, but just use colon and then the final index that you want to get. Here is a array X sliced starting from 0 to 5. Once again, you don't get the fifths, the element with index 5, you get element with index 4. And here, this picture basically shows how it looks like. You can slice elements starting from some index and up to the end of the array. Here is an image that shows you, and please look at the syntax that we have 5, colon, and then nothing. So when you don't write anything after the column, it will take all the elements up to the end. Slicing from some index to some index. One interesting thing, slicing, but I don't take all elements one by one. I'm doing some sort of jump between all these elements. So here is the syntax. For this case, when I'm trying to do X column, once again column, and then 2. This 2 means that some sort of delta, my jump, is not 1, but it's 2. So I'm starting from element 0. I'm getting up to the end of the array, and I'm doing jumps in 2. So I start from 0, then plus 2. I'm taking element index 2, plus 2 element index 4, and so on and so forth. Really useful syntax. So there will be many cases you will want to take elements from your array starting from some index, but don't take them just one by one, but with some sort of gap. Of course, this syntax has its own limitations. For example, this gap should be everywhere equal. So you can get with this syntax, for example, jump first in 2, then in 4, then in 75, and so on. So if you are jumping in 2, you are jumping in 2. Okay, once again, example of this syntax, but I'm starting not from 0th element, but from element number 1. And here is an example that shows you how to invert an NumPy array. Quite interestingly, you can make your jump -1. You tell to NumPy that you want to walk along your array backwards. So you want to start at the end of you want to start at the end and then walk to the front of the array. And here you make jumps with -1, which means that you take basically every element, but you are inverting their order. And one more example. Here I'm using, well, everything I could. So I'm jumping in -2. It means that I am inverting the array. My jumps are bigger than 1, which means that I'm leaving some elements out. So here you see the picture. And I'm starting not from the end of the array, I'm starting from some sort of index 9.
Sorry,
yes,
one question. When we are slicing, we are receiving a new NumPy array, like newly created, or it's kind of also referencing original one?
In many cases, you will get references. That's the interesting part. I will show you a little bit later what can we, when do we get references, when do we get copies. I will show that just in a moment. Yes. Okay, just 1 minute. I show you the same thing for two-dimensional arrays. Here it is. So once again, I can do all the same operations along every axis of the array. So if I have 2 axes, I can do that along 2 axes. If I have 3, 4, 10 axes, pretty okay. I can do everything with all the axes that I have. Here are examples for two-dimensional arrays, of course, because I cannot grow more than 2 dimensions for the array. So that's everything I can. So once again, example of taking not all elements, but some part of elements. doing that in sort of jumps. So once again, I have some long jumps along the array. I can fix one index, but take everything along some other dimensions. Very useful syntax. It's very often you want to get some part of your array and do something with that part. So for example, you have a two-dimensional array and you can treat that as a matrix that contains vectors. So some sort of vectors, some meaningful vectors can be stacked into the matrix. And you want to get one of those vectors and you want to do something with that vector. So for example, if you have a unitary matrix, you will have as the columns of that matrix, you will have some sort of vectors that constitute a basis for the space. And you want to get one of those vectors and do something with that vector. So it may be the case. So you are doing some sort of math on them. And this syntax will be very useful for you to get that vector out of there and to perform some sort of operations on it. So one more example here, I'm just leaving out one of the axes because it's the last axis of the array. So I have unwrapped my box, one of my boxes, but I left the other one. So here was a nice picture, for example, this one. If I unwrap the outer index, this 0, I will get some sort of boxes that constitute one-dimensional NumPy array. And this picture basically illustrates that case. If you want to get a column, you should do a little bit differently. So you are fixing the other dimension and you are taking everything along dimension, along axis number 0. And here is an example of inverting matrix. So you can use all that inverting tricks in your matrices, in your two-dimensional arrays, pretty the same way as you can use them in one-dimensional arrays. Okay, memory management. Yeah, that was the question, and I guess this part should just a little bit answer to that question. So once again, I'm having an array. So here is array x2. You see some sort of, it's not numbers, it's basically strings. I have put some strings into it. It's not like a very meaningful operation, but I wanted just to create some sort of better picture for you. So I want you to see which element is from which cell. And here is array x2. I'm doing some sort of slicing. So I have taken out a few elements from the array x2. By the values of these elements, you can pretty obviously see where they were in the initial array. And here I'm performing some operation. I'm setting a value to one of the cells of the array, of the x2 subarray. And here you see that not only x2 subarray changed, but x2 changed as well. So they are connected. So when you are doing that sort of slice, you are not creating a new array, but you are getting some sort of references to the old array. At least that's the way you can think about it. So you can think that you are just referencing some old elements. In the binary code, that can work a little bit differently. So for example, you can collect all that sort of slices that you wanted to do. And when you are applying some operation, you are just performing the slice and you are doing that operation on each element. Well, we will get to that, I guess, but you can think of it like having some sort of references to the previous array. I guess that will be pretty okay. Now, once again, what do we do? One of the methods is to perform copying. So here is x sub 2 array, and I'm just explicitly saying I want a copy of this slice. And when I'm getting this copy, when I'm changing something in it, I don't get any changes in the initial array. So here is the way how to work around that problem. So you should be careful when working with arrays, and because sometimes you have that sort of references to old elements, and changing something here may influence your arrays there.
Maybe
Yes, please.
and it works the same way if we are slicing with some bigger step also, or if we inverting it will reference the same without points.
Yes. I guess it will reference the same array. You will get new arrays when you are some sort. I guess when we are doing some fancy indexing, we will get new arrays. But when we are just performing slices on arrays, we will basically get the same good old array, and our changes will influence the initial array.
Okay. Thank you.
How do you think? Why? Why do we have this sort of troubles with arrays? So what I'm always teaching, there are no absolutely good solutions and no absolutely bad solutions. So everything has its pluses and it has its minuses. Of course, we all just felt that there is a big minus. We can get into some troubles if we don't keep attention, and we don't pay attention to our arrays, and we can change something that we did not intend to change. But now, what are the pluses?
C++. It's faster. Maybe.
Yes, it's faster. If you in many situations you'll be okay with that sort of referencing. That will be okay for you. So the time that you gain because you didn't copy the array and so on will be pretty valuable to you. So yes, you can win some sort of performance by not copying arrays, but instead you will need to explicitly declare when you want to copy your array. Okay, reshaping arrays. There are many cases when you want to change the shape of your array. So maybe you don't like that it's two-dimensional, you want to get everything into one dimension. Sometimes you want to do something else. So for example, make it from 1 dimension to 3 dimensions, and so on and so forth. You have a really nice operation for that called reshape. It takes a list or a tuple of numbers that will tell what kind of array do you want to get at the end. So how do you want to reshape your array? You should be careful because it will throw you an error if the number of elements in the array and your new dimensions do not match. So if I want an array sort of 3 by 3, I should be sure that my array has at least 9 elements. If it doesn't have 9 elements, or it has, I don't know, 10 elements, I will get into trouble. So I need 9 elements in the array because that's the shape I want to get at the end. So this operation looks, well, this way. What else? There are some, let's say, synonyms for some of the reshapes. For example, here is the 1-dimensional array, and I want to make one more dimension, but that will just contain all the elements. So I want it to have shape 1, 3. And here is the alternative way to do that. When I'm explicitly saying to the NumPy that I want just a new access here. So I'm sort of wrapping into a new box, and that box will contain everything that I had previously. And here you see how it looks like. Of course, I can have this new axis on some other place. So that's equivalent to reshape 3, 1. That was 1, 3, and here is 3, 1. In this case, I'm moving down to the individual elements, and I'm wrapping each element in this sort of box. It may be a little bit not very intuitive when you are just trying to do something with NumPy arrays, but well, I'll encourage you, if you feel that all these reshapes and all these shapes of the arrays, they are confusing you in some way, you can check our workbook on the GitHub, and there is the block of code with this kind of visualization. And I encourage you just to play around with the arrays, just visualize some of them to get the general idea how that works. So how all these reshaping, changing something in arrays, and how that works and how that looks like in some sort of more intuitive way. Okay, few more operations. Very often we want to get our array from many dimensions just to one dimension. So I want to adjust everything into one straight line. Here are two operations that will be quite helpful for us, flatten and ravel. They both give the same result, as you see. So array is just unwrapped into one dimension. But there is one interesting thing about it. Here you see I'm trying to set an element 0 from one of these arrays that I use flatten, so x.flatten, and changes in this array. Well, let's look better here. And changes in this array, they do not influence the initial array. So I performed y0 equals 123. You see a new number here, but nothing changed in x. Z, array z, I got it by doing operation ravel. And the difference is, if I do something with z, here I am setting z1 to 997, you will see that initial array changes. So sometimes the result of the operation may depend on the operation itself. So they may do like the same thing, but internally one of these operations, namely flatten, give you a new, basically brand new array. You can change that. You can do with that whatever you want, and nothing will change in the initial array. Or you use ravel, you get seemingly the same result, but the new array is connected to the old array, and changes in the new array will influence the old array. Of course, in practice, you use whatever you need. If you are okay with these arrays connected, you can use the latter, and you can gain some time because you don't need to copy all the data in memory. Sometimes these arrays, they get really large. So it's just, we are here operating with something like matrices 3 by 3 by, but in practice you can get some sort of array, I don't know, 1,000 by 1,000 or even more. So that will be quite painful operation to copy all that things from one place to another. Okay, one more example. For two-dimensional arrays, you have a transpose operation. Well, basically, you have transpose operation for any dimension of for any dimensional arrays, and I'm pretty sure I have some example for you. But yes,
excuse me, I think there is a tiny typo. Like in anywhere we see x equals np range 3 times 5 reshape 3 5. But we don't have such an array on the left. So I guess here, right here in the code, when you are drawing the table, Yeah, you're creating
Yes.
2 times 3 array, but here
Yes,
in
you're right.
in draw table function, when you're assigning a label, I guess there is a typo here.
Yes, you're right. I guess I should correct here 2 times 3.
And
And
reshape will go same
shape
way, right?
2, yes, 2, 3. Yeah, so
Thanks.
probably I was copying some old code and it remained. Okay, but I need to restart this part of code first. That will create me all the helper functions that draw my arrays. And now I should once again find where we were. Not here. And restart this part of code. Voila. Okay, thank you very much. I'll commit that after the lecture. Good. I guess here is the same problem, yeah? Okay, so copy pasting sometimes backfires. Here is the perfect case of that backfire. Here is some small syntax for 2D arrays only. When you are using x.t, that tells you that you want to transpose your array, but that's just 2D transposition. You can use transpose function for arrays of larger dimension. I guess there is some example down there, so we will get to that. Okay. Or no. So here is one more example, once again with wrong shapes. Let's fix it. Okay, I have an array X with dimensions 2 and 3, and I have a transposed array X transpose. Now I'm setting all the elements of Y to 500, and you see that all the elements of X have changed to 500. So once again, what conclusion do we make from all of this?
Transpose makes a reference.
Yes, transposition does not create a new array. So we are basically working with the old array. And here is an example of transposition in multi-dimensional array. Yeah, at least I have found it. So here is an array with some sort of shape 2, 3, 2, 3. And I want to transpose it. In most cases, we think about transposition in the context of two-dimensional arrays. So we are just thinking about some sort of matrices, and we are putting that matrix on this side. So just rotating it 90 degrees. But in the context of NumPy arrays, you can think about transposition as changing all that axes, changing their order. So you have your axis of the array ordered some way. So axis 0, 1, 2, 3, and so on. And you can reorder that axis and get a new array. So here's an example, some monstrous array, well, not monstrous, but at least quite big to be displayed on the screen. And I'm transposing, I'm changing the order of the axis, and I'm getting some sort of new array. I guess it's hard to grasp what do we get at the end of the day. So hopefully you wouldn't need to work with some sort of complicated arrays with many, many dimensions. But you should know that there is a mechanism that allows you to change the order of axes, and with that, you change your array. Okay, so arrays concatenating and splitting. So you can concatenate your arrays and you can split your array into parts. So here's just simple function, concatenate. You put into it a list of arrays you want to concatenate, and it does everything for you. So here is basically the example. You can concatenate your arrays with lists. They will be converted into array. So here is an example. You can do concatenation of multi-dimensional arrays. Of course, you should pay attention to their dimensions. They should be compatible with each other. But if they are compatible, you can concatenate them. And as you see, the concatenation is performed on the outermost axis. So here is the let's say the first box you will be unwrapping when you are getting some elements, and you are basically concatenating, you are stacking these outermost boxes, and here is the result. Okay, you can use, almost all functions in NumPy array have some additional parameters. So sometimes I will not show them because there are too many parameters and it's too long to get into all the details. You can always check the documentation of the functions. But almost certainly, for every function, you will get a parameter axis. This parameter defines along which axis you are performing some operation. So if you are doing something with the NumPy array, it can be treated as the operation along some axis. And most of such operations will have an additional parameter that will allow you to define along which axis you are doing that operation. For example, we were doing concatenation, so I have just called this operation concatenate. Without this part, with axis equals 1, we will get the result as previous. So it will just stack the outermost boxes that contain our elements. But when I define, I want to do that along axis 1, that will not more pay attention to the outer boxes, but it try to stack the inner boxes. Basically, it will work along axis number 1. Okay, two more similar operations like vstack and hstack. I'm not going into details here. You might just guess that these are operations for two-dimensional arrays, like concatenation, but for two-dimensional arrays. You have 2 dimensions, so hstack works along 1 dimension, vstack works along other dimensions. So nothing new, nothing special. Splitting arrays. Here is an example of splitting an array. So here is array X, and you are basically telling where and how do you want to split that. So in this case, I'm getting these splits before element number 3 and before element number 5. Well, number, I mean index 5. So if you are having an array, this way. So if you are having an array, this array is indexed. So index 0, 1, 2, 3, 4, 5, 6. And I'm sort of, when I'm splitting this array, I'm sort of making some walls between these elements. So I'm doing some wall, for example, here and here. And I am writing into that list, I'm writing indices on the right side of this wall. So I'm writing here 3. And here I'm writing 5. So I want to split my array before index 3 and before index 5. And what do I get at the end? So here is my example, and I'm splitting before index 3 and before index 5, and I get 3 different subarrays. One contains elements 1 to 3. They have indices 0, 1, 2. The second contains elements 99. They had indices 3 and 4. And the last one contains elements 3 to 1 that had indices previously 5, 6, and 7. So that's what I get at the end of the day. Okay, what else? I can split by number of chunks. So for example, I want to split my array into 4 chunks. I'm just saying I want 4 parts, and that will create me 4 equal parts of the array. Some modification of this function for 2-dimensional arrays like vsplit and hsplit. Well, nothing fancy, just the same operation for 2-dimensional array. And okay, and here is the crucial part that I wanted to show you, and maybe the main reason for using NumPy arrays. So, okay, at this moment, we know how to at least create some NumPy array. We know how to change an element in there. We can split an array and we can transpose it, so on. That's pretty okay. But what we want actually to do, it's performing some operations on the NumPy arrays. Performing these operations has a very large advantage in comparison to performing the same thing in Python. And the main reason for that is so-called universal functions. What does it mean? It means that you are not performing all that operations in Python. You are just basically creating a pool of instructions, what you want to do with your NumPy array. You are passing that into the binary libraries, and they will perform all that operations for you. So in some sense, you are trying to have both the flexibility of the Python and the performance of binary libraries compiled with some sort of, I don't know, C or C++ or whatever. So that's what you are trying to get here. And the universal functions, it's functions that are applicable to NumPy arrays, and that will be performed down there in the binaries. So basically what we want when we are writing some code with NumPy array, at the end of the day, we want to get a code that uses just universal functions. So we want as small as possible Python or just or let's say operations performed on the layer on the level of Python, and we want as much as possible operations performed on the level of universal functions, so down there in the binaries. So that's what we want. So here's an example for you. I called it slowness of loops. So here is the function sum arrays that takes 2 arrays and calculates its sum. So nothing fancy here. We are taking 2 arrays. We are performing summation. Here we get it. And for big arrays, when we have some large arrays, it takes some time. So here it took 400 milliseconds per loop. Okay. Now I'll try to use universal functions. So here I'm creating just 2 arrays. Once again, just some random numbers, nothing fancy. And I'm adding these 2 arrays. I'm using operator plus. Plus is overloaded for NumPy arrays, and it is not performed on the level of Python. So you don't get somewhere in the Python file something, some code like take element from this array, from that array, add and put into some array. No, that's not what happens. What happens is this sort of instruction, and maybe some more if you do something more with your array, they are packed together and they are passed to the binaries to be performed there. And I get the performance of this operation much, much bigger than I can get that in Python. So here is the time for adding two arrays, and I get just one, well, let's round it to even 2 milliseconds per loop. So what did I get from this? At least 200 times quicker than adding the same thing in Python. So it's really crucial for you to use universal functions to perform your operations on NumPy arrays. So when you are doing some sort of calculations and you know that you will deal with some large arrays with some big amount of data, what you want to do, you want to convert all your data to NumPy arrays and perform all your operations in form of universal functions. And in this case, you will get a really nice performance, and your operations will work quite fast. Here are presented some universal functions of the Python. So you see addition, subtraction, multiplication, so whatever you can expect that functions to be there. All the arithmetic. Of course, you have some more and more functions in the NumPy library, so you can check that documentation, or maybe I have even here some sort of code. But what I want you to tell, the first thing, the NumPy arrays, you can use them with some sort of different libraries. So you may want to check library NumPy or some other libraries that make your calculations parallel. You will get some more restrictions. When we went from lists to arrays, we had at least one restriction, yeah? So we need our array to contain all the elements of one type. So that was restriction number 1 when we were getting from lists to arrays. And restriction number 2, that our dimensions, they should be compatible. You can have a list of sublists, and it's pretty okay if your sublist number 1 has 1 element and sublist number 2 has 10 elements. That's pretty okay. With NumPy arrays, you can get it. You either have a NumPy array with dimensions 10 by 2 or 2 by 10 or something like that. And you will always have 20 elements in there. You can have 9 elements in there. You can have 15 elements in there. You should have 20 elements in there. So that's for the second restriction. With a little bit more restrictions, you can get some different libraries to work with your Python code. It's really simple, so maybe I will show you that at some point. So you can use, for example, NumPy to make your calculations parallel. That's great. And you will have a very similar syntax if you do something with neural networks. So for example, if you are working with TensorFlow or some other libraries, you will see that they have a very similar syntax to the NumPy arrays. And once again, you will want that whatever you do is expressed in the operations of that library. Why? Because they all are performed on the GPU, and you really want that everything you do is performed on GPU. You are just creating some package of data. You get that package there into the GPU, and then everything is performed there quickly, and then you just get the result. So that's what would you want. And you will get into similar let's say in similar situation to the NumPy array. So whatever we are learning right now may even help you in there. So its similarity will be beneficial for you if you get into that libraries. Okay, so one more example, creating some arrays performing multiplication. Please remember that that addition and multiplication are performed element-wise, so element by element. So if I'm having two arrays, so array number 1, array number 2, I'm performing, let's say, addition, multiplication, whatever you do, sum operation. You get, at the end of the day, you get a new array. And these operations are performed element-wise. So you are taking this element, you are doing plus, and you are putting into this cell. So here's how you get the result. You're just doing that one by one. Okay, what else do I have? One more table with lots of different mathematical functions. So these are, once again, universal functions. So you can use them on your NumPy arrays and get the performance of C++ code, basically. So that's really good. Okay, here I'm just showing how to use that functions. Once again, performed element by element. So nothing fancy. Okay, what else? We can have some operations like NP multiply that can put our result in some predefined array. So if you already have some array for your result, you can use parameter of the function out, and you can define that you want to put your result into that array. So once again, why do we do that?
Performance optimization.
Yes, it's always performance optimization. We want our program to run as fast as possible. Creating new arrays consumes time. If we already have an array and we can use it for our result, why don't we do that? That will save us some time. That's really good. Okay, here is one more example. You see that as out, I'm using a slice of array y. So here is a possible hint for you. Why do we want that slices to be connected to the old array? In some cases, you want the result of your operation to be put into a new array, but not into the whole array, but into some part of the array. And since all that slices are connected to the arrays they were taken from, you can use them as in parameter out or on the left side of the equal sign. So it's pretty okay if I write y, all that dots, all that colon 2 equals to something. And that something will be put into basically into y array. Once again, it's a way for performance optimization. So I can I can win some time with that. Okay, what else? Some operation like accumulation. I guess you know that it's some sort of running sum. So when you are getting through array and you are adding new elements and putting a sum of all the previous elements into a new cell. Really nice operation. You may want to have that if you have the problem of finding some sums of numbers in some segments of the array. And if you need to do that very quickly, the running sum is the algorithm that you may want to have. Well, I saw this algorithm, at least in practice, for two-dimensional arrays. When we are talking about images and we want to get something like integral image. So we want to have a sum of intensities of all pixels in some part of the image. And this sum will tell us something about that part of the image. So it was used for image recognition and so on. That was way before everyone got their hands on neural networks. So I'm not sure if anyone uses that methods right now. But that was basically the way of calculating very quickly that integral parts of the image.
Probably can be used for something like pooling in convolutional neural networks, when you also need to do like small operations on such operations on small sections of the picture. So maybe there.
Well, maybe that depends how it's.
Like, usually it's max pooling, but maybe it's important to have like this integral pooling.
Okay. Broadcasting. Well, how much time do we have?
Break maybe?
Yeah. Yes, I guess
it's about time that one lecture.
Yeah, I guess we can make a break and then we'll get to broadcasting and okay, so let's continue. So once again, we are dealing with NumPy. We are working with NumPy arrays. And basically in this section, I want to tell you what will happen if you are trying to perform some operation on arrays that have different shapes. Why is that of interest to us? So previously, I told you that when we are doing some operation on NumPy arrays, we are performing that operation basically element-wise. So I'm taking element by element, some sort of array, and I'm performing that operation on that array. Or if I'm, for example, adding two arrays, I'm taking elements synchronously from that arrays, and I'm performing that addition or subtraction or division, whatever I do. But here is the tricky part. In some cases, you may want to have the ability of operating with arrays that have different shapes. And the first problem is getting, let's say, some sense of that operations. So what do we want from that operations? What do we expect from them? And the second is how our NumPy and Python, what do they do in this case? So what do we get at the end of the day? And here is a motivational example for you. So I have an array. So let's take some simple array, 0, 1, 2, 3. And what I want to do is add 1 to each element of the array. So I want to just take each element of the array and do +1. What can I do basing on the things I told you previously? I can do a cycle through the array and add +1 to each element. That's perfectly possible. But what I get is, well, I get the correct result, so it's okay. But this is time-consuming operation. I'm doing an iteration through an array on the level of Python. I don't want that. I want to avoid that. So it's possible, but better not do that. What else can I do? I can try to use universal function. But the problem with universal functions, well, if you are only basing on the things I told you previously, is that you need to erase and you will perform your operation element-wise. So to perform that operation element-wise, I need to create one more array, set each element of that array to 1, and then perform addition. That will give you the correct result, but once again, it's not what we want. Why? Because we are losing time on creating a new array, on very useless array, because all its elements are equal. It's just number 1 everywhere. And this is time consuming, this is memory consuming. Of course, we don't want that. So what we want at the end of the day, it's somehow instruct our NumPy that I want to take this array and I want to add some constant to each element of the array without creating any additional arrays, without performing any cycles on the level of Python. I just want to pack all that instructions, as I did previously with my universal functions, pass it to the binaries, and get out of that binaries a result. So that's what I want. And in this case, to deal with such cases, we have broadcasting. In some cases, broadcasting is quite intuitive. So I guess that you will use it eventually here and there, and it will be quite intuitive for you. In some cases, it may get very tricky. But I'm afraid there's no other workaround to do with that trickiness. just, I don't know, just to explore what dimensions do you have in your arrays and what new arrays are you getting out of there. So that's the only way. Maybe visualize somehow. I will show you a function for visualization I have for you. So once again, I have written that for you so you can see some more or less nice pictures. But only practice will get you really to master all that broadcasting. That's the only way. But anyway, at least some cases, at least some simple cases will be good enough for us to do what we want. And here is the simple case number 1. Once again, I have my array 0, 1, 2, 3. I want to add 1 to that array. What I do, I just write a plus 1. As you see, 1 is not an array, it's just a number. But it understands what I want to do correctly. Here is some sort of picture for you. You can think of it like making that number 1 into a new array of 1s and then performing that addition. What I want you to pay attention to, whatever I drawn here, it's just a mental picture for you. It's not what happens in the real binaries. Nobody will create a new array with just 1, so that's not what happens. It understands what you want. It will perform all that addition and do all that for loops and so on in there and perform everything correctly. The result will be the same as if this 1 was transformed into array and then the 2 arrays added. But in practice, it works quite quickly because it's not what happens, but happens something a little bit different. But the result you get is exactly as if you turn this 1 into some sort of array. And not only numbers. Of course, just adding numbers, some sort of transforms them, quote unquote, into these virtual arrays and adds to the initial array. But you can add arrays of different dimensions, one to another, and still get the correct result. Here's one more example for you. I have some sort of array that contains numbers 0 to 8. This is this is a two-dimensional array, 3 by 3. And I'm trying to add something to it, and whatever I'm adding basically has the same rows. So once again, if I'm performing this operation, I don't want creating that new two-dimensional array. It is really redundant because all the new information we have, you can get it just from 1 row. So we don't want to create 3 rows in this case, or in some other case, you will create, I don't know, 1 billion rows. You don't want that. You want just 1 row. Can you do that? Yes, you can. Broadcasting will transform, let's say, quote, transform, unquote, this 1 row into something like this, into a two-dimensional thing, and add them two together. And here is a picture, a mental picture you should have when you are dealing with this sort of broadcasting. So here is a new row. I want to add it to some sort of matrix. And this row is, in this case, so virtually copied. And you are performing the addition as always, element by element. Broadcasting can be applied to each of the operands of some binary operation. For example, here I have 2 arrays. One is just one-dimensional array, so nothing fancy. The other one is unexpectedly a 2-dimensional array, but quite an interesting array. Yeah, as you see, we have axis 0 that is indexed from 0 to 3. And we have axis 1, and we have just one element along that axis. So it's some sort of vector column in some sense. When we are adding that, once again, a broadcasting happens, and you get a new result. And here is a mental picture for you. Once again, how did this broadcasting happen? So the first array, in the first array, we have copied the column a few times, and in the second array, we have copied the row a few times. And we add them, and we get the result. Just once again, element-wise. And here are the exact rules. Well, I should tell you that it's a little bit maybe complicated to use these rules, but that's the way it is. And most cases, I think you will just do some experiments and and get the idea how the broadcasting is working and whether.
So usually just to try if it works or not.
Yeah, absolutely correct. It's just faster to try. Does it work or does it not work? Does it give you the result you want to get, or it just throws out some garbage and you don't want to get that result? So rule number 1, if the two arrays differ in their number of dimensions, the shape of the one with the fewer dimensions is padded with ones on its leading left side. What it means, if I am adding a one-dimensional and a two-dimensional arrays, we need to do something with that one, with their dimensions, because we want two arrays with equal number of dimensions. What else can we do? So we are taking the array with lower number of dimensions, which is logical because we don't want to throw away some information, yes? So we can do something with the two-dimensional array. We don't want to throw away some rows or columns, so we are keeping it the way it is. But we are taking the one-dimensional array, and we are adding some new axes to that array. This addition of axes does basically nothing, but just some sort, as I drew you, create some new wrapping, some new boxes. But information stays the same. Now, they have along that directions, that new directions, they will have some shape. And here is a tricky question for you. What is the shape of that array with the fewer dimensions along its new dimensions? So according to rule number 1, I should add some new dimensions to the array because it's lacking some. Okay, I'm adding them. He gets a new shape. What is its shape along that new dimension?
The shape of secondary.
The array I am trying to broadcast. So I'm trying to add two arrays. Yeah? Okay. Let me draw that. So I'm trying to add a one-dimensional array and a two-dimensional array.
Sorry, Vitaly, can you move the board a bit to the right? Because yeah.
Okay. So now I'm trying to perform some sort of broadcasting. So here are my two arrays. So array, I don't know, X and array Y. I'm trying to add them to get something of it. But I can't add them element-wise, at least because they do not have the same dimension. So what I'm trying to do right now, I'm trying to follow the rules of the broadcasting to transform them somehow, at least transform them in some virtual sense. And then after this transformation is performed, I will get two arrays with the same dimensions, with the same shape that I can add element-wise. And here is the rule number 1. If two arrays differ in the number of dimensions, Do these two arrays differ in the number of dimensions? Yes, of course. This is one-dimensional, this is two-dimensional. Good. What says this rule? The shape of the one with fewer dimensions. This is the one with fewer dimensions because it has only one dimension. This one has two. Okay, so this one, what we are doing with it? It is padded with ones on its leading left side. It means that I am changing the dimensionality of this array from 1 to 2. From 1 to 2. But how do I do that? So I need to add some dimension. So its shape right now is just one, well, not one, it's 5. And I want to transform that into 1, 5. So when I draw you all these pictures that we have, I draw them like some sort of boxes, yeah, that we are in some sort of boxes and our elements are contained within that boxes. And I'm wrapping and unwrapping these boxes. So in case of two-dimensional array, what I draw you a series of boxes that are wrapped inside of some bigger boxes, and so on. And when I was getting some element, I was just unwrapping them box by box. Here I'm getting to a new shape, so it means that I need to wrap this thing into some sort of new box. Now the rule number 2. If the shape of two arrays does not match in any dimension, the array with shape equal to 1 in that dimension is stretched to match the other one's shape. So now I have array shape 1, 5. They still don't match. So what it means, I'm using the rule number 2, and I'm saying that this array should be stretched along that dimension that is equal to 1. Please note that there is a number 1. If I had array with dimensions 2, 5, and I was trying to do something with it and array 5, 5, that wouldn't work. Only if I have dimension 1. This dimension 1 came from the fact that I was trying to use the rule number 1. So now I use rule number 2, and I'm transforming this 1 into 5. So I'm trying to do 5, 5. How do I do that? I'm copying this thing, basically, along this dimension. So I need to create more big boxes.
But why 5? We need 4 maybe.
And inside the old information just copied.
Sorry, we didn't hear.
We probably need 4. We probably need 4. I don't know, like boxes to sum.
Yes, we need 4 because here was not 5 by 5, but 4 by 5, yeah. So here is 4, yes. Yes, you're right. This is 4 by 5. And now this array is, I have transformed it into 4 by 5 as well. Of course, this is just a mental picture. So what we need to see in our head when we are thinking about all this, all these rules. In practice, that's all performed in the binaries in a way that basically does not need any of those copying and creating some redundant arrays. But that's a way to think about it and to understand what we will get out of this operation.
May I ask
Yes,
one question? First rule was like that the shape of this fewer dimension padded with ones on leading left side. Padding with ones means like that we are raising dimension or what?
Yes, we
I
are
thought
adding
that
dimensions.
Okay, I thought that if we're padding with ones, we like adding ones somewhere. Or...
No, it's not like adding ones to the array itself. It's adding ones in the shape of the array. That's the example I was showing you on the desk. So rule number one, well, let me draw that once again. So why not? So here was our initial array. And it had dimension just 5. So that was its shape. Yeah, so shape 5. Nothing more, nothing less. Here is the array we wanted to add to. It has shape 4, 5. So now we are talking about shapes. We see that this array has a lower number of dimensions. So now I am padding its shape with ones on the left side. So I am transforming this 5. I'm transforming it into what? On the left side, I'm adding ones. If we had here array with the shape, I don't know, let's say 5, 7, 8, 10, 5. Once again, I will take this array and I will add here some 1, 1, and so on. So many ones as I need to match the number of dimensions in here. So if this is something more like something more complicated and multi-dimensional. So the idea is to pad the shape of the array, so adding some new empty axes. Okay. And after the axes are added, you match their size with the rule number 2. Yes. I thought there was a question. No.
No. I said understood. Yes.
Okay. Good. What else do I have? Some sort of transformations. Once again, I'm performing adding a matrix with a vector. Here we perform all that operations with our rules, number 1 to 3. 3 just describes that when sizes disagree, let's say too much, we are raising some sort of exception. So nothing, nothing fancy here as well. But you can reshape your array before performing some sort of operation in a way that will enforce some different results. For example, when I'm adding this 2-dimensional array and this 1-dimensional array, you see the addition is performed. You are adding some sort of row to each of the rows of the array M. But what if I want to add a column? I don't want to add row, I want to add a column. I can reshape X on my own just by adding a new axis to it and add them once again. When we added it as it was, we should have used the rule number 1, transform it into a new array. So it will be, this is array with shape 3. Rule number 1 will make from it array of shape. Of which shape will it make it? Rule number 1, who can tell me?
1, 3.
Yes, 1, 3. 1, 3. And we will get this result. But if I will on my own make from it an array of shape 3, 1, I'm doing that consciously. You see that I'm using all these new axes and so on. So that I'm enforcing that operation on the array. So I'm getting x, I'm getting shape of the x 3, 1, and I add it once again to the same matrix. I will get a different result. Why? Okay, let's put it another way. Is the rule number 1 applicable in this case?
No. No.
No.
It seems.
Yes, perfectly correct. It's not applicable because they have equal number of dimensions right now. So rule number 1 is not applicable, but they still don't match in their shapes. So what do? We apply rule number 2. And rule number 2, it performs along the axis of length 1, it performs some sort of virtual copying. And if you do that virtual copying along the axis of length 1, you will get copied your elements 1 to 3 this way along, along the axis. And when adding them together, you get a new result. This result is equivalent as to adding a column to each column of the matrix M. So some sort of adding new axes or some sort of reshaping arrays before performing binary operations is the way to influence the result and to enforce some flow of the operation. So that, well, you will probably use that in your practice. So whenever you want to add, well, not a row, but a column to a matrix, you will probably do this sort of trick. And if you are dealing with some more and more complicated arrays and something like that, you will probably use even more extensively this kind of operation. Okay, here I'm trying to add just 2 arrays with different shape, and you see that an exception is raised, so nothing interesting. Here is a function from NumPy, broadcast arrays. I'm not sure if anyone uses that in any of the production code, but when you are doing a debugging, at least on some small arrays, you may want to use this function to trace how your arrays are broadcasted. So if something strange happens, you are performing some operation on the arrays, and you don't want to retreat to doing all that cycles in Python and all that for loops, what you may want to do, you may want to call this function broadcast arrays, get some new arrays, and look at them. So what happened? How did it broadcast your arrays? And here's an example for you, some initial arrays, and how will they be broadcasted in case they will meet together in some binary operation. So it doesn't basically anything depend on that operation. So whatever you do, you add them, you subtract them, do whatever you want. Broadcasting will be performed the same way, and here is the result as it will look for you. Okay, here is an example of broadcasting many-dimensional arrays. I even didn't bother to draw them because the image is too cluttered with numbers. I just printed out their shapes, and you see how the shapes have changed. You see dimensions that were 1 in one of the arrays. When they don't match with the dimensions of the other array, they are stretched, and the information is like virtually copied. Okay, so some examples of broadcasting in practice, a really practical situation. You want to draw some function, and here I'm drawing that function with matplotlib. We will talk about that library a little bit later, but what I want you to know now that it's a nice library to draw basically different plots, and you may want it to use for some visualization of whatever you do. And here an example that I'm plotting data, and this data is basically a function, a two-dimensional function on x and y. And here is the step along x. So I am starting from 0 and going to 5, and I'm doing some sort of 50 points of 50 probes of that x. And the same thing I'm doing with the axis y. And now I need to calculate the value of this function on the grid of x's and y's. And of course, the I don't know, the most simplest way, as you might think of it, is just creating all possible pairs of x's and y's, and then calculate the function on that pairs. But when you are dealing with NumPy, you can use all that broadcasting things to make everything, well, run smoothly. So for example, I'm just doing sine of x, and sine is applied to each element of the x. If I need somewhere x and y to be in one function, I just multiply them. Broadcasting transforms that into a matrix. So this thing, basically, how many dimensions does it have?
2.
Yes, it has 2 dimensions. When I'm adding 10 to that, once again, broadcasting works, and 10 is added to each element of that 2-dimensional thing. And cosine is applied to each element of that 2-dimensional thing. And how many dimensions has this thing?
1, but it's broadcasted.
Yes, it has 1 dimension, and then it will be broadcasted. So when I'm calculating cosine of x, I'm taking cosine of each element of the array x. Then when I'm performing multiplication, I'm doing once again a broadcasting, and that what I have calculated, that row of data, is then added to each row of the matrix of cosine x times y. And then once again, a broadcasting is performed to add this sine to the power of 10. So a lot of broadcasting is performed in this formula. In some sense, it looks very intuitive. So that's probably the way you will write this formula if you are doing just some math. So not some Python, not some plotting, just math with a piece of paper and a pen. And basically, the broadcasting rules are tailored in a way that they are trying to perform all the operations so that they look like naturally for you. So this is quite natural way to write this formula, and you will get the result that you expect. Of course, it's a real world, and in practice, you will more or less often get into the situation that something will work not as expected. And it's really nice to have, if not some full understanding of what is happening right there, because it's, well, it's quite complicated to get all the things into your head, but at least to be aware of some problems that you might get into when you are dealing with all these broadcasting things. Okay, I guess it was a very complicated part. The rest is, I guess, quite simple, the rest of what we have here. I will just very briefly show you. So here is the table of different operations. It's some sort of aggregation operations. What it means that they take as an argument the whole array, and they give you a result as some sort of number. Well, it's not always you can influence what they get you, but the idea is like this. So you are giving them an array, they are giving you some overall information on that array. So for example, NP sum. So you are getting some sort of sum from that array, or you are getting some mean value, or standard deviation, or variation of that array, so on and so forth, some minimal, maximal, so on. They have so-called non-safe version. As you know, that when you have a floating point data in your array, there may be some values like not a number or something like that. And if you want to deal with them, you can use a non-safe version. Of course, you can find them in array and substitute them by something, or somehow remove them and so on, but these functions may make your work a little bit faster. Example of summing data in the array, so nothing fancy. Once again, the arguments, since these operations are dealing with the whole array, they will often take an argument called axis, and you can tell them along which axis you want this operation to be performed. So for example, if I'm trying to get a sum, and I am giving a matrix to this function, it may be the case that I want to get the sum of all elements of the function, or maybe I want to get a sum along some dimension. So for example, sum in the rows or sum in the columns, whatever. And I can influence the result by setting axis. Basically the same thing for all the rest aggregating operations. So you are setting the axis and you are getting the result along that axis. Really helpful thing. Okay, so here is time measurement for Python min and NumPy min for some large array. You see 102 milliseconds and 400 microseconds. I remind you that microseconds second is 100 times smaller than a millisecond. So it's a really big deal. The
1,000 probably.
1,000. What did I say? 100. Okay, yes. 1,000 times smaller than a millisecond. So it's really beneficial for you to use that operations from NumPy, but not from the Python itself. Okay, so minimal operation, the same. Masks and comparison. The interesting thing, you can from your NumPy array create another array that will contain true or false depending on some condition. So here is an example when I'm trying different conditions on array X, and as a result I'm getting different arrays of truths and falses. Later you can use these arrays well, for different purposes. Most cases, you will use these arrays to extract certain elements from the array you are basically working on, so from this array X. Maybe you will want to extract them from some different array. That may happen. So I guess there is an example of that. So what you can do with that arrays? First, I can create that array just using some Boolean operations. So that's okay. I can check how many of them are non-zero. So if there is some condition and I want my array to pass that condition, I may want to check whether all elements pass that condition or not. In this case, I have NP any and NP all. So I'm checking that all elements pass that condition. I'm checking that at least one element passes that condition. Or I can count the number of elements that are passing that condition well, and then do something or do not. So that depends. This type of code you will see in cases when you want to check your input information. So you are having some input and you want to check that input, whether it satisfies certain requirements that you have. For example, you're going to divide by that numbers and so on, and you don't want to get some infinities or something like that. So probably you may want to check that your numbers are non-zero, or maybe you need your numbers to be positive or something like that. Works on arrays of different dimensions. That's okay. NP any once again has parameter axes, so you can ask this question if if at least one element passes my condition or all elements pass my condition along some axis of the array. That's good. And these are, and you can use Boolean arrays as masks. Before that, yeah, I should show you this thing before. If I am intending to use my array as a mask, it's really good to have some Boolean operations on that mask. And here's an example for you of operation OR, and operation NOT. So I can take two Boolean masks, and I can take AND, or I can take OR I can take NOT. So that depends. A really good thing, because I can write, with this syntax, I can write x smaller than 3 and x bigger than 1, for example. Here is an example for you. So I'm getting a Boolean array from some sort of range. Please note these brackets. There is some caveat in the precedence of operations that will make it not work if you don't use brackets in here. So I'm not sure why but that's the way it was created. So you should write brackets. Okay, what else? Here is an example of usage of that array. So, okay, we can create Boolean array. We can use few arrays to create some U array, Boolean array. So x less than 3 and x bigger than -5 and x not equal 0 and so on. Now you want to use that for something useful. And here is an example. I have array x and I have array of, let's say, indices, if I can say that contains true and false, and true stays on the places of the elements I want to take out of the x. So I want to get a new array, and I want to get into there some elements of my initial array, and I'm basically setting flags. This element I'm taking, that element I'm not taking. And here is the syntax. You just write x, and in square brackets, you put your different array. It should have the same shape as x, and it should contain true and false, and which will basically say which elements are you taking and which elements you are leaving out. Here is a bit more useful example. You have two arrays that are connected to, let's say, some sort of vehicles. And you have the one array containing horsepowers of that vehicle, and you have the other array that contains a number of cylinders. And for example, this is your data set. And for example, you are interested whether vehicles with 4 cylinders have more or less horsepower on average than vehicles with, let's say, 6 cylinders. And here is an example how to do, let's say, the first step in that analysis. So what do you want to do first of all? You see that your vehicles with 4 cylinders and with 6 cylinders, they are mixed up in your array. So you want to separate them. So that's the first thing you want to do. So I want to get my 4-cylinder vehicles to the left and 6-cylinder vehicles to the right. So that's what I want to do. And how do I extract them? And with this syntax, you see that basically cylinders equals to 4. I'm basically creating a Boolean array that contains true and false. It contains true whether there is 4 cylinders, and it creates false whether it's not. Then I'm using this array right here in place, so without any additional code, to extract information on horsepower from the array HP. So I'm using one array to create that true-false and quite a different array to extract data. And here is my new extracted array. So here I have horsepowers for cars with 4 cylinders only. Now I can apply some functions like mean value, standard deviation, variation, whatever I want. I can do some analysis. But at least I have, as a first step, I have extracted the information I was interested in into a separate array. Yes, please.
About Boolean arrays, are they also referencing those arrays which we used to create them? Like if we create Boolean array, for example, with cylinders, and then change some value in those cylinders, will Boolean array be different after that?
Boolean array or array of horsepower that I have indexed with that Boolean array?
If we created a Boolean array with cylinders and then changed some value in cylinders, then will Boolean array which we created be different after change of cylinders?
No, it will not change. It will not change.
Okay.
It wouldn't change because it's a brand new array.
Okay, so it's not
a brand new array of different type. Yeah. A more tricky question: is there any connection between initial horsepower array and this array? I guess it's creating a new array. But basically, I can tell you that off the top of my head. I think, yeah, it creates a new array here as well. And if we check that in the code, probably we will see that it's a new array. I don't know if it still works, so maybe we can even check that quite quickly. So here is okay. Okay, so 70, 80, 74. Let's say yeah, as you see, even these two arrays, like horsepowers and horsepowers indexed by cylinders equals to 4, they are disjoint now, so they are separate arrays. And this example basically demonstrates that, so it's illustration for that case. And I can even ask you once again a tricky question: why? So all the things are designed by humans, so they were thinking about something. So why did they it this way, not the other way around?
Because we can't guarantee that. We can't guarantee that parts of this array will go one after another in original array, and because we don't it's not a list of references, but it's actually values stored one after the other. We just can't use original array. We need to create new.
We basically reuse.
Maybe it's also faster just to not reuse Boolean array each time, but create new.
Well, I'm about right now. I'm not about Boolean array, but this initial array of the horsepowers. Well, the thing is, just think for a moment, how would you write that code on your own? So you are a creator of a NumPy library, yeah? So you're sitting at such nice desk and you're thinking, so what should I do in that NumPy library to make it work quite fast and to be to be useful for us? Whatever you and if you think about, let's say, slices, you can think, okay, I can write some complicated code, and in that code I can incorporate some information. So I'm taking like elements starting with this index and ending at that index and doing jumps and so on. Anyway, you will be doing in your code some sort of cycle. So this information gets into the binaries. But anyway, in binaries, you are performing all that cycles. You can get away with that. Anyway, operation should be performed. And there is no big difference whether you write your cycle from 0 to the end of the array, whether you are doing some sort of e equals plus equals 1 or e plus equals 10. So you can get the information from the outside and incorporate that into your cycle. But what is happening when you are using some Boolean array to extract information?
We should reference it each time.
It's random in some sense. The information you are getting, there is no pattern in that information. So you are getting some random chunks of your original array. And to perform some operation on that random chunks, you should somewhere store information which chunks you are taking. So to describe fully slicing, you need only 3 numbers. So that's a manageable amount of information, just 3 numbers. Where do you start? Where do you get? And what is the step you are doing? When you are getting information with a Boolean array, you need the whole array to get the correct information. And if you didn't create a copy of the original array, you will forced into somewhere storing that Boolean array that you were extracting basing on. You need to store that Boolean array, and every time you will need to check with that array to go through each element of that array and check whether you are using that element or you are not. And this is a large overhead on your operations. So it's much more reasonable to create a new smaller array, lose some time on copying information from one array to another array, but at least you can forget about that Boolean array and everything else and just work with the new array. So you are not more tied with all that Boolean things. And what will happen if I will do some slices of that new array? You can imagine how horrible your code becomes if you are everywhere you are taking all that Boolean array and every time you are re-extracting all the elements. That's horrible. And that takes really a lot of time. So it's really more beneficial for us just to create a new array and copy the information in there and forget about all the horror of working with that large Boolean array. Okay, the last thing to say, so-called fancy indexing. So here is, once again, here is some sort of array. And I want to extract some information from there, so some part of it. The boring way will be creating a new array and putting some extracted elements. The more fancy way is creating a new array of indices and passing them to X. This example is not very nice because I could have done the same thing with slicing, but you can imagine here any numbers in any order, and you can pass them in square brackets to your array and extract information from there. So that's what you get at the end of the day. So you have like two ways. The first way, you are creating some large Boolean array, and you are extracting information from the cells where that Boolean array says you true, or you can explicitly describe the indices you want to extract from your original array. So some examples, that's really, I'm not getting into that just because it just repeats the example above, just for more dimensions. Combined indexing, it just means that you can use fancy indexing together with just normal indices or with slices and so on. So it's okay if you mix up all these types of indexing, that's pretty okay. So with a Boolean array and so on. Of course, for each axis, you choose the way you are working with it. So with axis number 1, I'm just extracting one element from there. With axis number 2, I want to use a Boolean array. Axis number 3, I want to use fancy indexing. And number 4, I will do slicing. And the axis number 0, I just left as it was. So that's pretty okay. You can do that. With fancy indexing, you can modify values. That will be okay. So here is an example. Some nooks and crannies I'm not getting into. Function sort and arc sort. That's the last thing I will show you today. Well, you can guess. Sometime we need to sort our array, and NumPy provides us with a really nice function sort. What you may not be aware of, that we have a function arc sort. That's the function that returns you not a sorted array, but the indices of the initial array in the order you should take elements of the array to make it sorted. It looks a little bit convoluted, but a really useful function. So here's an example. When you are taking array X, you are doing arc sort, you're getting all these indices, and you can check that when you take X square brackets I, you will get the initial array sorted. Why do you want to use that? In some cases, you have few arrays with information that is connected between these arrays, somehow interconnect. For example, like that vehicles with horsepowers and number of cylinders. And you want to sort them basing on one of that arrays. So for example, I want to sort my vehicles basing on the horsepowers they have. So from the lowest to the highest. If I just sort array with horsepowers, I will lose the information on cylinders, because cylinder array will remain unsorted, and information in it will be not any more connected to the information in the array with horsepowers. So what I will actually do, I will use function arc sort to get all these indices basing on the array of horsepowers. Then I will use these indices to sort my array of horsepowers and array of cylinders. And I will be pretty sure that the order in which I put information about cylinders is the same as the order I put information about horsepowers. So that is the, let's say, more correct way to sort arrays if you have some information that is connected between them. So you may want to use that with some data sets. Yes.
I have a question. It's not particularly related, but can you create custom structures and create NumPy arrays from it? So, for example, instead of creating two arrays, you create just one array, but with structures, with two fields.
NumPy allows you to create such things. It's called NumPy structured arrays.
Mm-hmm.
So there is a different way when creating this sort of connected arrays, but it's really it's really often you will get in practice into the situation when you already have separate arrays. For example, when you are dealing with some data set, you will get separately information on features, some large array, and information on their labels. So you are doing some sort of supervised learning, and you need information for training about features and about classes. And you get them as two separate arrays. You just load that this way from somewhere server outside, and there's nothing you can do with that. And in this case, you will need to deal with that data. Of course, you can convert it first to some sort of your internal structures and do something with them. But probably that will suffice just to perform this sort of trickery to keep them ordered in the same way. So array of features and array of labels. So I think we will see that in practice somewhere, because that really happens sometimes. Okay. Of course, if you are creating your own software, and you are free to use some different methods to avoid this sort of thing. So maybe some classes, maybe using NumPy structured arrays. I don't want to get very deep into that. So that's a little bit more advanced topic, but you can check that at the end of our notebook. Yeah, and the last nice demonstration, it's calculating nearest neighbors with that sort of functions we have. So in the code, we use different functions like sorting and so on. You may want to check that a little bit later. Once again, I'm not getting very deep into it because it's a really trivial method when you are just comparing.
We will talk about it later anyway.
Yeah.
Later
So
in the course.
Yeah, so maybe we'll meet it later in the course. So with that being said, I think it's everything I wanted to tell you. So basically, what did we came up to? So in conclusion, so NumPy library is really powerful for numeric computation. It can save us a lot of time, so it's really good. So it's performed with binary libraries that are much quicker than Python code, so we may want to use it as much as possible. The keystone are universal functions. So they process the whole array without any need from us to write some Python loops and so on. And almost all Pythonic scientific packages use NumPy. So whatever you do, if you get into some sort of science, you calculate something, you will maybe 99.9% you will need NumPy. So I think that's everything. If anyone has some questions, comments, I'm